Quadratic equations, the lazy mathematician's approach. What a strange title for an algebra video. In just a few minutes, I'll tell you what that title means. But first, let's talk about what a quadratic equation is and how to solve one. A quadratic equation is an equation which can be written in the form ax squared plus bx plus c equals 0, where the a, b, and c are constants. We will talk about 3 ways to solve a quadratic equation: factoring, completing the square and using the square root property, and using the quadratic formula discovered by a lazy mathematician. Factoring. Not all quadratic equations can be solved by factoring, but here's an example of one that can. Suppose you're asked to solve 12x squared minus 17x plus 6 equals 0 by factoring. How would you do it? Well, you can attempt to factor by trial and error, but if that takes too long or is too hard, you can use a technique called splitting the middle term. Comparing this equation, 12x squared minus 17x plus 6 equals 0, to the general quadratic equation, ax squared plus bx plus c equals 0, we can see that in this problem, a is 12, b is minus 17, and c is 6. To split the middle term, the minus 17x, we want to find 2 numbers whose product is equal to a times c, or in this problem, 12 times 6, which is 72, and whose sum is b, which is negative 17 in this case. Since the product of the 2 numbers we are searching for is positive 72, and the sum is negative 17, both of the numbers will have to be negative. We can search for the 2 numbers systematically as indicated in the table. Negative 1 times negative 72 has a product of 72, but the sum would be negative 73, not negative 17, so that doesn't work. Negative 2 times negative 36 has a product of positive 72, but the sum there is negative 38, so that doesn't work. Negative 3 times negative 24 doesn't work. Negative 4 times negative 18 doesn't work. 5 won't go into 72, but 6 will. But negative 6 times negative 12, that too has a product of positive 72, but the sum there is negative 18. That doesn't work. Finally, look at negative 8 and negative 9. Their product is positive 72. And the sum of negative 8 and negative 9 is negative 17. So negative 8 and negative 9 are the numbers we are looking for. What do we do with those numbers? We rewrite the original equation by splitting the middle term. We're going to rewrite negative 17x as negative 8x minus 9x. That's how we're using the minus 8 and minus 9 that we found. So 12x squared, we replace minus 17x with minus 8x minus 9x plus 6 equals 0. And then we can factor by grouping. We group the first 2 terms together, 12x squared minus 8x, and group the second 2 terms together, the minus 9x plus 6. We factor out the greatest common factor from the first 2 terms. That would be 4x, and what's left is 3x minus 2. 4x times 3x is 12x squared. 4x times minus 2 is minus 8x. From the second 2 terms, we can factor out a negative 3, and what's left is also 3x minus 2. Minus 3 times 3x is minus 9x. Minus 3 times minus 2 is positive 6. Notice that we now have a common factor, 3x minus 2. When we factor that out, the other factor is 4x minus 3. So we end up with 3x minus 2 times 4x minus 3 equals 0. Once we have the product of these two factors equal to 0, we know that one of the factors must be 0. If we set 3x minus 2 equal to 0, we get x is 2/3. If we set 4x minus 3 equal to 0, we get x is 3/4. So 2/3 and 3/4 are the two solutions to this particular quadratic equation. We've solved it by factoring. But some quadratic equations cannot be factored, and we can solve those by another technique called completing the square and then using the square root property. Let's look at an example. Solve 4x squared plus 16x minus 1 equal to 0. This one cannot be factored, so we're going to complete the square. What are the steps to do that? Here's our original equation. Step 1 says to move the constant term to the other side of the equation. So if I add 1 to both sides, I end up with 4x squared plus 16x equals 1. Step 2 says divide each term on both sides of the equation by the coefficient of x squared. In this case, that's 4. So 4x squared divided by 4 is x squared. 16x divided by 4 is 4x. 1 divided by 4 is 1/4. The third step is to take half of the resulting coefficient of x, square it, and add that to both sides of the equation. So half of 4 is 2, and that squared is what I'm going to add to both sides of the equation. Half of 4 is 2, 2 squared is 4. So I now have x squared plus 4x plus 4. On the other side, I added the 4 to the 1/4, and you can combine 4, which is 16/4, plus 1 more fourth to be 17/4. We're going to express the left side of the equation now as a perfect square. We added what we needed to add to make the left side a perfect square. That's why the technique is called completing the square. X squared plus 4x plus 4 is the same thing as x plus 2 times x plus 2, which is x plus 2 squared. Now we can take the square root of both sides, and we will have x plus 2 is plus or minus. The square root of 17/4 is the square root of 17 over 2, because the square root of 4 is 2 in the denominator. Whenever you take the square root of both sides of an equation, you have to introduce a plus or minus sign. To finish the problem, we now can easily solve the x by subtracting 2 from both sides of the equation. We will have x equals minus 2 plus or minus the square root of 17 over 2. If you would like to write that expression as a single fraction, you can rewrite -2 as the same thing as -4 divided by 2, and then rewrite this with the common denominator of 2, and you'll have x is minus 4 plus or minus the square root of 17 all over 2. And those are the two solutions to this particular problem. Well, that was quite a lot of work to complete the square and then use the square root property. What about the lazy mathematician's approach to solving quadratic equations? Well, some bright person said, wait, instead of going through this whole process of completing the square over and over again for each new quadratic equation that we want to solve, let's just complete the square for the general equation, and that will give us a formula to quickly solve any quadratic equation. And behold, there came the famous quadratic formula. So you see, usually we think of being lazy as a detriment, but sometimes if being lazy can inspire you to discover an easier, quicker way to do something, it can be an asset. How did the quadratic formula come to be derived? Well, let's look. Let's take the original general quadratic equation, ax squared plus bx plus c equals 0. And we're going to go through the exact same steps that we just went through in the previous particular equation to complete the square and take the square root. Remember, we started by moving the constant term to the other side of the equation. So we subtract c from both sides of the equation. Next, we divided every term on both sides by the coefficient of x squared. In this case, we're dividing every term by a. Ax squared divided by a is just x squared. And then we would have plus b over a times x equals negative c over a. The next step that we did in the previous specific example was to take half of the resulting coefficient of x, square it, and add that to both sides of the equation. So we're going to take half of b over a and square it and add that to both sides of the equation. That works out to be 1 times b is b, and b squared is the numerator. 2a, the quantity squared, well, 2 squared is 4, and a squared then is in the denominator. So we end up with b squared over 4a squared on both sides of the equation. The next step says that we want to express the left side of the equation as a perfect square, and we want to simplify the right side. So the square root of x squared is x. The square root of b squared over 4a squared is b over 2a. The middle sign is a plus sign, so we want a plus sign here, and it's this quantity squared. X plus b over 2a squared would be x plus b over 2a times x plus b over 2a. If you FOIL that and check it out, you'll see that you do get x squared plus b over a times x plus b squared over 4a squared. Over here on the right-hand side of the equation, we want to combine these two terms, add them together by getting the common denominator of 4a squared. Minus c over a is the same thing as minus 4ac over 4a squared. So I can rewrite the right-hand side of the equation as b squared minus 4ac over 4a squared. Now I want to take the square root of both sides, and that will give me x plus b over 2a equals plus or minus the square root of this numerator over the square root of the denominator. The square root of the denominator is just 2a. And then finally, I solve for x by subtracting b over 2a from both sides of the equation. And there is my quadratic formula. For any quadratic equation written in the form ax squared plus bx plus c equals 0, the solutions are x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. You don't want to have to go through rederiving this formula every time you want to do a problem. So it's helpful to just memorize this final result and apply it to solving quadratic equations. The lazy mathematician has done all of this work for you and given you this result to be able to quickly find solutions for quadratic equations. If you look at the part of the quadratic formula that is under the square root sign, the b squared minus 4ac, that has a special name. It's called the discriminant. If b squared minus 4ac is greater than 0, there are going to be two distinct real solutions for your quadratic equation, and they would correspond to the x-intercepts on the graph of the equation y equals ax squared plus bx plus c. If your discriminant, b squared minus 4ac, equals 0, there'll be only one solution for the equation, and it'll be a real number corresponding to a single x-intercept on the graph of y equals ax squared plus bx plus c. That graph will be a U-shaped curve called a parabola, and this single solution to the quadratic equation will correspond to the vertex of the parabola when the discriminant equals 0. If your discriminant is less than 0, the solution to the quadratic equation will be two imaginary numbers that are complex conjugates of each other, Because they're not real numbers, the graph of y equals ax squared plus bxc plus c will have no x-intercepts. Here's some examples. Here's a quadratic equation. 2x squared minus 7x minus 4 is 0. So a is 2, b is -7, c is -4. If we apply the quadratic formula to solve this equation, x would equal minus b minus -7 plus or minus the square root of b squared minus 4 times a, which is 2, times c, which is -4, all over 2 times a, so 2 times 2. If we simplify this, minus -7 is 7. And if you look at the expression under the square root sign and do the arithmetic, it works out to be positive 81 over 4. The square root of 81 is 9. So we have as our solution 7 plus 9 over 4 and 7 minus 9 over 4. 7 minus 9 over 4 is -2 over 4, or -1/2. 7 plus 9 over 4 is 16 over 4, which is 4. So the two solutions to this quadratic equation are -1/2 and positive 4. If you graph y equal to 2x squared minus 7x minus 4, that graph will be this U-shaped curve that looks like a parabola, and its x-intercepts will be -1/2, or -0.5 as a decimal. The other x-intercept will be positive 4. Notice that the discriminant here, the number under the square root sign, was 81. 81 is greater than 0, and when the discriminant is greater than 0, we do indeed have two distinct real numbers that are solutions to the quadratic equation, and they're the x-intercepts of the graph of that quadratic function. Let's look at another example. Suppose you have the quadratic equation x squared plus 6x plus 9 equals 0. Here a is 1. This is like 1 times x squared. B is positive 6. C is positive 9. If we use the quadratic formula, the solutions to the equation are x equals minus b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So simplifying, we get minus 6 plus or minus this expression under the square root. If you do the arithmetic, you'll find that it equals 0, and the denominator 2 times 1 is just 2. The square root of 0 is 0. So we end up with a single number, -6 over 2, which equals -3. Since the discriminant, the number under the square root sign, is 0, that tells us there's only one real solution to the equation. That solution is -3. And if you graph y equals x squared plus cx plus 9, you get a parabola that does indeed have only one x-intercept at -3. We call this turning point of the parabola, where it changes from decreasing to increasing, the vertex of the parabola. Here's a final example. Take the quadratic equation 3x squared minus 2x plus 4 equals 0. Here a is 3, b is -2, c is positive 4. Using the quadratic formula, x equals minus b plus or minus the square root of b squared minus 4ac, all over 2a. When we simplify, minus minus 2 is positive 2, plus or minus, again doing the arithmetic under the square root sign, gives -44, all over 6. The discriminant here is -44. Because the discriminant is a negative number less than 0, it tells me that the solutions to this quadratic equation are going to be complex conjugates. You can actually simplify this. The square root of -44 is It's the same thing as the square root of -1. Square root of -1 is I, times 4, square root of 4 is 2, times 11. The 11 is left under the square root sign, all over 6. If we factor a 2 out of the numerator and the denominator, the 2 divided by 2 is just 1, so that cancels. So our final answer is 1 plus or minus I times the square root of 11 all over 3. Or you could write it as 1/3 plus or minus 1/3 times I times the square root of 11. Those are the complex conjugate solutions to this quadratic equation. Again, the discriminant was -44, a negative number, meaning there's no real solutions. And if you graph y equals 3x squared minus 2x plus 4, you can see that this parabola is opening up. Its vertex is here above the x-axis, so there are no x-intercepts. Hopefully this helps you understand how to solve quadratic equations and to appreciate the work of the lazy mathematician who completed the square of the general quadratic equation for you and derived the quadratic formula, so that now you have a quick and easy formula to apply to solve these types of equations.